Okay, I hope I'm audible. Just a second. I think they are thinking. Okay, I hope I'm audible. So, welcome to your sixth discussion session in Mechanical Behaviour of Materials. I am Pragyandipta Mishra, and I am a research scholar from Department of Applied Mechanics and Biomedical Engineering. Today, we'll be discussing about dislocations. We'll be understanding some concepts related to dislocations in detail, and we'll be solving some problems with regard to dislocation to understand those concepts better. So, with that out of the way, let's begin our discussion for today. So, in the last class, when we talked about dislocation, there were few things that we actually talked about, right? We talked about how these dislocations are essentially something that describes why our theoretical shear strength, essentially that what we calculate using formula and other things, is way higher than experimentally observed values of shear strength or yield stress, etc. Right? So the reason why these dislocations are there in the first place is because when the grains are formed, the material is formed, there is some sort of inherent stresses being present within the structure, which manifests itself out in the form of a defect known as dislocation. Right? This is not due to grains growing out or things like absence of a particular atom or presence of certain atoms. No, these are one-dimensional defects. Right? So the major reason why this happens is because there is some sort of inherent stress that the material has undergone previously, and that manifests itself out in the form of dislocation. Now, these dislocations are already there. That is what we already have proven, right? We have seen that experimentally that the value of yield stress that we have observed is way lesser than the theoretical values that people usually see. Essentially, we also saw that there are two major types of dislocations, right? There are edge dislocations and screw dislocations. However, there was something that I talked about in the last class, right? That this edge and screw is something that we have decided to actually enforce in order to describe or solve problems with regard to dislocation much easily, right? Because if we are not doing that, then it will be very difficult for us to classify dislocations and solve the various components of dislocation, the various factors that we need to understand with respect to dislocation will become much more difficult for us. However, in real life, that is not the case. Okay. In real life, usually we will see dislocations to be in many different shapes. You can see that dislocations will essentially be curved. They may take shapes which are very irregular. They may be looped. They may abruptly start, abruptly end, etc. and etc. So let's start with this topic about how the dislocation could be in real life. So let's say we are given a crystal structure. Essentially, let's say that this is extending along the plane, like into the plane that I am showing from the top. So this is like a top view of that entire thing, the crystal structure. So this is a 2D image of that. Now, if we want to see, like if you're seeing a dislocation through like some type of microscopy, which is able to actually show the dislocation, what we will observe is that the dislocation essentially is not one dislocation. So we will not have like one plane of atom missing like this, and then one dislocation being present, something like that. No, we will not have like that. We will have dislocation in different shape and form. Okay, so one of the ways in which we could actually see dislocation being present could be that we can have certain atoms being displaced from their original position. For instance, this atom, the one I am circling in red now, gets displayed to this position. This atom gets displayed to this position. this atom gets displayed to this position, this atom gets displayed to this position. Okay. And similarly, all the other atoms below it also follow suit. So what has happened is, initially when the crystal structure was like this, now has changed to a new shape like this. Let's draw it so that. Okay. So this is how the dislocation will manifest in materials that you will see around you. Okay, if you observe them under microscopy, you will see this kind of dislocation. So essentially, what will happen is you will have a dislocation line, which is going from this atom here, where the bending is starting. This atom here, and it will go something like this. Okay, this is your dislocation line, the one I have shaded. Okay. Now at different points in the dislocation line, we can see a relationship between the dislocation line to the slip vector or the Burgers vector, right? And depending on what kind of angle it forms, we can classify it as screw dislocation, edge dislocation, or having a characteristics in between screw and edge. So at this point, maybe, let's say if it has become, let's say the Burgers vector is always downwards, okay? The Burgers vector for this dislocation is always downwards, or the slip vector. So here you can see the dislocation line has become almost almost horizontal, right? And the Burgers vector is vertical. So this point would probably be edge. While this point here, the Burgers vector is also downwards, while the dislocation line is also downwards. So we can say here at this point we can observe screw. Right? So let's say this is point A, this is point B. So at point A you have let's take it as U. That will be easier. So your U is parallel to Burgers vector B. So this is screw dislocation. While at point B, your U is perpendicular to Burgers vector B. This is edge dislocation. Again, do not get confused when I'm saying Burgers vector or slip vector, they're one and the same thing. Do not get confused that in the video sir might be talking about slip vector, but here I'm talking about Burgers vector. They're one and the same thing. Okay, it's just a choice of like convenience, whatever you feel like saying. So you can just choose whichever one. So essentially, if you have a dislocation something like this, okay, at one point you are having, say, like I said, here you are having edge dislocation, while here you are having screw dislocation in between this region. So from here to here, this region is essentially your mixed dislocation characteristic. So it is neither screw nor edge, but having behavior which is in between screw and edge. Okay, we'll be understanding about this mixed dislocation also as we go forward. How do we classify or how do we characterize this mixed dislocation, and how are we able to find specific values that we need with respect to each dislocation? How can we do that for mixed dislocation as well? We'll see that. But yeah, for now you can just understand that mixed dislocation is something that is neither fully screw or fully edge. It is showing characteristics which is in between screw and edge. Okay. So this is how you will see dislocation being manifested, right? However, when we are looking at dislocation, we have to also understand that dislocation is not something that can keep going and going, right? There has to be an end to a dislocation. So how can a dislocation end? So this is something that you can think about. A fundamental characteristic for any dislocation is that it has to end somewhere, right? So how do you decide where the dislocation is going to end? So essentially, if a dislocation starts, can it end suddenly, abruptly? Can it end? Or does it need to have some certain features or certain properties being present within the material system for it to end in that particular state? So essentially, if a dislocation has started, right, you cannot say that dislocation will suddenly end or suddenly terminate at some particular point without any reason. There has to be something that a dislocation has to uh, fall into or has to flow into, right? It is something like, if you want to think of it in a much more easier sense, you will think something like how um, a river will just keep flowing, right? And it will not just stop suddenly. The river cannot stop suddenly. Something has to stop the river, or it will just fall into the ocean at the end. So dislocation should also behave the same way. Okay. So if you are looking at dislocation lines within a crystal, within a single crystal, okay. So there are three ways that people have found that the dislocations essentially terminate. Okay, these are the three ways that people have seen over the years. People have seen in different types of microscopy how dislocations can terminate. So let's write it down. The first way people have seen is that there is a surface. The dislocation has encountered a surface. So essentially, what is happening is, if the dislocation is keeps on going, at some point it might hit the surface of that crystal. When it hits that surface, then the dislocation might suddenly terminate. Now, what do we mean by surface of a crystal? Is there something specific that we are talking about when we say surface? So, if we are talking about surface of a single crystal, it could mean that the actual surface of the entire structure has been reached. Meaning that if we have a 3D structure, right? Now the dislocation keeps going and hits this surface, like this face it has hit. So it has hit an actual surface, and therefore the dislocation has to terminate. But surface does not only mean the actual surface of a particular material system or the particular body that we are examining. Surface could also mean other things. For instance, when we are looking at a single crystal, we might have a surface in the form of a grain boundary. Now we'll understand what grain boundaries are later on, but just to understand, just to get a glimpse of what grain boundary is, you can think of it as something like the crystals being present. This is one crystal. This is crystal 1. This is crystal 2, like this. So this boundary that separates crystal 1 and crystal 2 is known as grain boundary. So this also forms a surface, right? Because that is the surface where your crystal 1 ends and the crystal 2 begins. So that also represents a surface. Now this grain boundary essentially is formed when the crystal grows in a particular way. When you heat the crystal and start cooling it down, grain boundaries are something that are formed. We will discuss about how these grain boundaries are formed, etc., in the later weeks when we discuss grain boundaries as a defect. But yeah, so grain boundary can also form a surface. So there can be surfaces in different ways. Okay, there could also be a surface in this way where you have one crystal of a particular type and then you have another crystal of another type. So something like if you have precipitation in the crystal, okay, or something like that, those can also lead to formation of a new surface, and therefore your dislocation has to end there. Okay, so surface could just does not mean the surface of the entire body, but also means a new surface that is starting from that particular point. So things like grain boundary, precipitates, etc. could also form a surface. Okay. The second way a dislocation can also end is branching. Now, what do we mean by branching? Essentially, dislocations have certain properties um, which is inherent to it. So, for instance, if you are looking at a dislocation line that is percolating through a particular body, why is that being formed? Now, there are stresses, inherent stresses, like I said, right? There are inherent stresses which are present in the body. Now, these stresses are not able to escape out of the body. So, it has to manifest itself in the form of a dislocation, which means that a dislocation by itself does not form, because a dislocation is formed due to an accumulation of stress or presence of extra stress in the body. So, in the end, at the end of the day, any body, any system that we are looking at, right, that this is something that is common across not just material science but across anything, any body that we are looking at. By the rules of thermodynamics, any body will try to minimize the energy that is present within the body, right, to go to a lower energy state. That is the major reason why anything happens, right? Any reaction, any deformation, etc. Anything happens because the material is trying to reduce the energy within its structure. Now, with respect to dislocation also, the material will sometimes try to reduce its energy. And one way to manifest that is to form branches. So instead of having a very long dislocation like this, sometimes what the dislocation will do is that it will branch out into 2 or 3 maybe dislocations. Okay. Now this branching out has certain specific rules. Okay. Let's say this is the Burgers vector for the original dislocation B1. Okay, it's the Burgers vector. And B2 and B3 are the Burgers vector for the branched out dislocation, the new dislocation that have been formed. Okay. Now this dislocation B2 and B3 will have a vector sum which is equal to B1, so that the dislocation vector is conserved. Okay, so this is something that you can also note down. Sigma Bi is always equal to 0. Okay, or that is dislocation vector is conserved. Now this is something that has to be followed whenever dislocation is branching out. Okay, because if the vector is not being followed, the Burgers vector or the slip vector is not being followed, then that means that the dislocation has terminated and now we have moved on to a new dislocation. Okay, so you always have to follow this Burgers vector sum whenever you are looking at any dislocation. Okay, so by branching out, so this is another way in which a dislocation can terminate. Okay, by branching out. So why we are saying that the new dislocations are not same as previous dislocation, because they are having new Burgers vector or new slip vectors, right? B2 and B3 are different from B1. So therefore, branching will result in dislocation getting terminated. Okay. The third way in which a dislocation terminates is by formation of loops. Let me just add a few pages. Okay. Now, what do we mean by loops? So sometimes what happens is a dislocation line might just go around and just hit itself at some point. So then the dislocation has to terminate because it has fallen into something else, right? So the dislocation has just formed a loop. Now the loop does not mean that it has to complete the loop, like it has to start and end at the same point. No, a loop could begin at any point and end at any point within the dislocation, right? But what has happened is the dislocation has terminated suddenly. Okay, and this part of the dislocation, this line of the dislocation could be terminated at a surface, or this side of the dislocation. So basically what I'm saying is point B is ending at a loop while point A is not ending at a loop. It is ending at a surface, or it is ending, or it is creating branches here or something like that. Okay, So essentially, one of the ways dislocation can also terminate is at a loop, as a loop. Okay, let me just, okay. So finally, few important things that you have to keep in mind is dislocation by itself cannot terminate inside a crystal. Okay, it needs one of these three ways in order to terminate within the crystal. Okay. So by itself, dislocation cannot terminate within the crystal. It needs one of these three ways. Okay, either it needs a surface or create branches or form loops. Okay. Uh, one another important thing that I already talked about when I'm talking about branching, of course, that Burger's vector for a given dislocation has to remain constant, irrespective of the orientation of the dislocation. Okay, dislocation can orient anyway, it can curve anyway, but the Burger's vector associated with that particular dislocation has to remain a constant. Okay, so irrespective of the orientation of the dislocation, the Burger's vector has to be conserved. The moment Burger's vector changes, it means that the dislocation has ended. Okay, so a new dislocation has started. Either it has branched out, formed a loop, something has happened, the dislocation has ended. Okay, so these are some of the ways in which dislocation can terminate. Next, let's understand the different dislocation properties. Okay, so we are still understanding our fundamental characteristics of dislocation. So let's understand some dislocation properties with respect to edge and screw. Okay. Okay. So what is the relation? So let me write here edge and screw. This will be easy. Move it a little bit down. Okay. So first thing that we have to see, of course, that goes without saying, which we have already discussed. What is the relation between U and B, or the dislocation line and the Burger's vector? So in edge, U is perpendicular to B. In screw, it is parallel. Right? Next thing is slip direction. In which direction will the slip happen? What do we mean by slip direction? Slip direction is basically the direction in which slip happens, or the slip vector, right? So it is same as the Burger's vector. So you can just say parallel to the Burger's vector. Okay. What do we mean by slip? slip just means that the material has moved along that particular direction. That particular vector is what is defining in which way the slip is happening. Okay, in both the cases, slip has to happen along the Burgers vector only. It's just the dislocation line is going parallel or perpendicular to the Burgers vector is what we are concerned with. But a slip is always happening parallel to the Burgers vector. That is something that you have to keep in mind. The direction of dislocation line movement a dislocation can only move in a particular direction, right? If what do we mean by dislocation moving? So in edge, for instance, like I can take example of edge dislocation. Let's say we have like this kind of edge like structure initially, right? Now we have applied a stress so that a dislocation starts. Right, and now this dislocation will keep moving through the material. Right. So the direction in which the dislocation can move is also determined by what kind of dislocation we are looking at. Okay. However, a dislocation can only move, if you think about it, the dislocation can only move perpendicular to the dislocation line, right? Because the entire dislocation, let's say that this is my dislocation, this entire thing is the dislocation. I cannot move this in the plane of the dislocation line, right? Because then the dislocation is not moving. The dislocation has to move this way or has to move up down, right? If this is the dislocation line, this entire the pen I am holding is the dislocation line, right? This is the dislocation movement or this is the dislocation movement, right? So it has to be always perpendicular to the dislocation line. So in the case of edge, if it is perpendicular to the dislocation line, then it will be parallel to the Burgers vector, right? Or perpendicular to the dislocation line. However, in screw, Burgers vector and dislocation lines are parallel to each other. So if it is perpendicular to dislocation line, then it has to be perpendicular to the Burgers vector as well. Right? Okay. So then we have to look at if the dislocation within edge and screw can be further divided into what kind of dislocation they are forming, right? So are we having some sort of positive or negative dislocations depending on what kind of way these dislocations are created? So in edge, there are no types of dislocation. All dislocations are the same type. Okay, so you can say that they are not physically distinct. Okay. While in screw, they are actually physically distinct. And I think in the previous week, this concept was discussed. They were known as RHS and LHS for screw, right? RHS, right hand screw, and left hand screw. So these two are the two types of screw dislocation depending on which direction the screw dislocation is moving in, or which direction it is actually getting created, in which direction it is getting created. It can either be RHS or LHS. At the end of the day, it does not matter whether it's RHS or LHS. Whenever you're solving a screw dislocation, you're writing equations with respect to screw dislocation. It does not matter whether it's RHS or LHS. It will have the exact same way, like you'll be solving them the exact same way. It is just a choice of it is just convenience so that we know that in which direction the screw dislocation has progressed. Okay, it is a matter of convenience only. finally, process by which the dislocations may leave the slip plane. So what do we mean by leaving slip plane with respect to a dislocation? The dislocation are lying on certain slip planes, right? For instance, okay, let's look at this edge dislocation only that I've drawn here, right? This is the plane in which the dislocation is lying, right? How can it leave this plane? If I'm looking at this edge dislocation from the top, okay, let's say this is my edge dislocation, okay. If I'm looking at this edge dislocation from the top, so it is going into the body, into the medium, okay. So from the top, this edge dislocation will look like a defect, a small defect, okay. How can it leave that particular plane is what we are now looking at. So there are different ways it can leave. It can slip to a newer plane, right? So it can slip like this, or it can climb, it can go up down, right? So that is also leaving the slip plane, it is moving to a newer plane. So in edge dislocations, what has been observed is that they usually climb, while screw dislocation will cause cross slip. Okay, so this is the way they leave that particular slip plane. Okay, so this is a property of the dislocation, but whenever you are looking at any real life examples of dislocation, because they show a mixed characteristics, they will sometimes climb, sometimes cross slip, depending on which is feasible or which has which is essentially leading to them reaching a lower energy, right? Because they're trying to minimize the energy. So depending on the particular situation, in real life, the dislocation can either climb or cross slip because they are showing mixed characteristics. However, edge is the only one which climbs. Screw usually cross slips. Okay, so that is something that you can remember. Okay, so one last thing before we start deriving different equations with respect to dislocations. One last concept. We talked about loops, right? So let's understand those loops in detail. Okay. So a dislocation loop can be of two type. Okay. Sorry, dislocation loop. One in which the entire dislocation is not concentrated with one type of dislocation. Okay, so the entire loop. So let's say if this is the loop. At different points in the loop, you will have different types of dislocation. Okay, so say this is my Burgers vector. Okay, now at this point, my dislocation is the dislocation line is in this direction, right? At this point, it is in this direction. At this point, it is in this direction. At this point, it is in this direction. So, if I label this as say point A, point B, C, D. So what I can say is at A and C, this Burgers vector is parallel to the perpendicular to the dislocation line. So it is edge, right? So this is edge. While at B and D, dislocation is parallel to the Burgers. Dislocation line is parallel to the Burgers vector. So it is screw. So essentially what we have seen is that Depending on whether the Burgers vector is parallel or perpendicular to the dislocation line, we can characterize within the loop which parts are edge character, which parts are showing edge character, and which parts are showing screw character. Okay, the any other place in between this loop will show a mixed character. It will neither be edge nor screw. However, there is another way in which the loop can be formed. Now, instead of the Burgers vector or slip vector being in the plane in which the loop is existing, this time the Burgers vector is perpendicular, right? So it is something like this, like it is going into the body or it is coming out from the body. So in each case, at every point on the dislocation line, I will see edge characteristics, right? Because my Burgers vector is always perpendicular to the dislocation line at every point. So I'll just see edge everywhere. So this type of loop is known as prismatic loop. And it has only edge characteristics. Okay. So essentially you can have only edge or you can have a mixture of edge and screw. You cannot have only screw. If you think about it, in screw dislocation, Burgers vector are always parallel to the dislocation line. Now when you're forming a loop, how will you form a loop when the Burgers vector is parallel to a dislocation line? You cannot form a loop, right? So you cannot have only screw loops. Therefore, dislocation loops can only exist in one of these two forms. Okay. So now let's move on to the next topic, which deals with how to construct dislocations. Okay. So this is given by a man named Volterra. Okay. I think it's 1A, maybe 1A. Construction. 1 hour through. Just a second. Okay. Now this construction is used to draw things like dislocations, disinclinations, etc. Okay. Now we'll not talk about disinclination. Essentially, disinclinations are like angular openings. It is not like dislocation where you have a one-dimensional defect being present. Disinclination are used for different purposes. This is not a defect kind of thing that we're looking at. So what we're concerned with is only dislocation. Okay. So how do we construct a dislocation with this Volterra construction? Okay. So before I construct this, okay, let me draw this first so that you can understand this better. Right. So if we have a body like this, actually let me use a different pen. Okay. And I am putting a cut here. Let's say I am putting a cut right here. Okay. And this leads to, let's use a different pen again. Putting a cut right here, leading to Let me just draw it again. I think it did not come correctly. Let's get the cut first so that it's clearer. Okay. So now this one ends here. Okay. So essentially what is happening is I'm putting a cut, a translationary cut along, let me draw the axis. So let's say this is my X, then Y is on this direction and this is my Z. Okay. I'm putting a cut along the X direction, and then I can translate the way in which I'm moving, like moving the two halves once I've put the cut. Okay. So depending on the way I'm translating it, I can form either edge dislocation or screw dislocation. So why we are talking about translation with respect to dislocation is because dislocation is essentially a translatory motion, like a translatory defect that is formed in the material system. So if it is an angular defect, then it will be a disinclination. Okay, so that is why we are not concerned with disinclination. We are more concerned with dislocation because it's much easier for us to solve problems with respect to dislocation. Okay. So once I've cut this way, if I am, let's say I'm just drawing it this way, way too big. Okay. So this is my cut region. Okay. This is the bottom. Yeah. Okay. So I've cut and I've moved them apart. So I moved them in, translated them along the y direction. I've moved them apart, right? So this leads to the Burger's vector being perpendicular to the dislocation line, right? So if my Burger's vector, the slip that is happening, the direction in which these two halves are moving, the slip that is happening, okay, is moving in the y direction. So if this is my xyz, right? So my slip that is happening is along the y direction. So Burger's vector is along the y direction, but the dislocation line is along the z direction, right? So u is along this direction, right? So this is edge dislocation. Now what if I slip, if I move it along the x direction? Again, my dislocation line will be along the y direction only, but I moved it along the x direction. So again it will be perpendicular, and therefore again it will form an edge dislocation only. So let's draw that and see how that will look. Okay. So Now let's move this little bit inward. Right, so what I've done is I've slipped it inwards now along the x direction. So in x direction I am slipping it, so that is the direction in which my Burgers vector will be, while my dislocation line is again along the z direction. So again it is an edge dislocation only. However, if now I am slipping it along the y direction, okay, sorry, z direction. So what I'll do is I will draw this first. So instead of moving this inwards, let's move this outward. Terminate this here. Yeah. And then create okay. Okay, so I've flipped it inwards. So essentially I'll have this thing and this thing ending here. Okay, so I've slipped it inwards. So my Burgers vector and my dislocation line both will be along the z direction. So therefore this is how we can construct screw dislocation using Volta construction. Okay. So depending on in which direction the slip is happening, whether it's in the x, y, or z, and whether it's parallel or perpendicular to the dislocation line vector, we can say whether it's edge or screw. Okay, so these are the ways in which you can create this, like construct a dislocation, and then use different equation to solve the dislocation. Okay, so now if you want to calculate the stress and strain field, because that's what we're interested in mechanical behavior of any material system, what we're interested in is the what is the stress and strain associated with that particular material, particular defect, etc. Right? So if you want to calculate stress and strain, which is fixed around the screw dislocation, why? So how do we do that? Okay, stress and strain field around a dislocation. Now, why do we talk about stress and strain field? What is the reason behind it? For instance, like let's look at edge dislocation. Okay. So if I have 5, then we have 4. So now what has happened is there is a dislocation being present here, right? In edge dislocation. What has happened due to that dislocation? We have an extra half plane here on top of the dislocation, right? Here we have an extra half plane. But on the bottom, we don't have that extra half plane. The presence of this extra half plane on the top part will lead to compression here, right? Because you're trying to squeeze in an extra half plane in between the structure. While the bottom part will be experiencing a tensile kind of load from the top. Why? Because this layer has lower number of lesser number of planes, so the bonds will be closer together. However, because the top part is having extra half plane, this one also has to accommodate that. So this will be experiencing a tensile or tension kind of force, right? So essentially, what is happening is on top will have compressive, while bottom will have tensile kind of load, kind of stress field. Okay, and as we move away from the dislocation, the field will vary in values. Okay, it will get smaller and smaller as we move away from the dislocation. It will be more concentrated around the dislocation. Okay, similarly in screw dislocation, when we look at any material that has undergone a screw dislocation, okay, so if there is any material that has undergone a screw dislocation like this, what has happened is the material has got sheared, right? When what is happening in screw dislocation, you are seeing a shearing kind of motion, right? So this shearing will cause some sort of deformation again in the material. Okay, and that shearing is stored in the material as a form of stress. Now, what are these kind of stress and what are this kind of deformation is what we will try to find out. What kind of fields are associated with this dislocation is what we are trying to find out here. Okay, so let's start with screw dislocation. Okay, let me just write it so that. So in screw dislocation, what is happening? We are having initially a structure like this, a shape like this, right? If you're looking at it from a 2D point of view. Then when we are shearing, the entire body, like if I'm looking at it from top, okay, I'm shearing it like this and I'm looking at it from top. So it is shearing like this, moving like this, right? It is moving like this. One is moving this direction, one is moving this direction from top. So from top, how I will see it is, I will see something like this. Right? That's how I'll see it. This will be equal to my Burgers vector, right? And the direction, this entire thing, let's assume it to be 2 pi r. Why? Because I've taken the Volterra cylinder and I've opened it up. Okay, I've opened this Volterra cylinder and I'm looking at it from top. I've opened the Volterra cylinder. So the circumference of a cylinder would be 2 pi r. So that's what I've taken. While, just a second. Yeah. Sorry, this is not rooted. Okay. Yeah. So I have taken this Volterra cylinder and I'm trying to create, I'm trying to accommodate this screw dislocation within itself, right? So how do I look at this screw dislocation? Because Now I don't have stress values or I don't have strain values. But what do I have? I have a deformation that has happened in different direction, right? Now I know along the x direction for a screw or along y direction also, we will not have any deformation. So those things will be 0. But along the z direction, I can write some theta by which this turn has happened times the radius of that particular thing, right? Theta r as my new value by which this 2 pi r has rotated. Okay. So theta r is the new value divided by 2 pi r, which is the original. This will give me the strain along z direction. Okay. Now this r here represents this Burger's vector b, right? Here, this b. So I can rewrite this as theta b divided by 2 pi r is equal to u. Now what is this theta essentially in terms of angular displacement that we are looking at in any shearing mechanism? What do we tell that theta is equal to? It is equal to tan inverse of y by x, right? So finally I can write u is equal to b by 2 pi r tan inverse of y by x. Deformation along the y direction divided by deformation along the x direction. Okay. Now what can I so sorry, this is deformation, this is not strain. I was saying strain by mistake too. This is deformation along the x direction, so z direction. So now if I want to write the strains along xx, yy, zz, now I know along xx, along yy, along xy, and then zz also, and yy, xy, zz will be equal to 0. Right, so the remaining strain, the only strain which is remaining, will be equal to half of du x by dz, right, plus du z by dx. This is from the basics of the strain that we have learned till now. Now this is 0, of course, because ux is 0, so this is 0. So only thing we are remaining with is half of duz by dx. So if I rewrite that part, I will get E of xz will be equal to minus b by 4 pi times y divided by x square plus y square. Okay. I've skipped some steps in between, but yeah, like you can differentiate that particular expression with respect to x and you'll find this as the answer. So you'll get minus b by 4 pi sine theta by r. So this is my like strain along the xz direction. Now strain along the yz direction, similarly I can write by differentiating with it like this thing with respect to y, uz with respect to y, right? I can rewrite this as b by 4 pi cos theta by r. Okay. Now these are engineering strains, but how do we find true strains from here? Let us assume that the strain that has gone into forming this distance is very, very small. Okay. So if the strain values are very, very small, then my epsilon xy is equal to, sorry, epsilon xz, I am writing that. Exz, and my epsilon yz is equal to EYZ. Right? So I can write the strain tensor for this particular screw dislocation. Will be something like 0, 0, epsilon xz, then this will be 0, 0, epsilon yz, then epsilon xz, epsilon yz, and 0. Okay. This is my strain tensor for screw dislocation. Now that we know strains, we can find stress from there, right? Because we know epsilon ij is equal to 2 times g. Sorry, sigma ij is 2 times g is epsilon ij, right? Or stress is equal to 2 times the shear modulus times epsilon ij. So in a similar fashion, we can write. Okay, let's just write down the expressions first. Sigma yz is equal to gb by 2 pi, because 4 pi, so 2 will get cancelled. It's cos theta by r. And sigma xz will be equal to inside of the pages. Sigma xz will be equal to minus gb by 2 pi sin theta. And our shear stress matrix will look the same as strain matrix. Okay, let me draw it. So 0, 0. Right? That's how my stress tensor would look like. Okay, stress tensor for screw dislocation. So essentially, what we are having are dislocation something like this. For xz, it will look something like this field will look something like this. Okay, so this is sigma xz. Even epsilon xz will look like this. While for yz, it will look something like this. So this is sigma yz or epsilon yz. They will look like this. The fields will look like this. Okay. One important thing that you have to note is that these stress fields or stresses do not look symmetrical. However, on the tensorial form here that we are seeing them in matrix form, it looks kind of symmetrical, right? But here on the field wise, it is not looking symmetrical. The reason for that is when we are constructing these stress field or strain field, we are constructing by keeping Volterra construction in mind. And Volterra construction is cylindrical in nature. However, we are representing the stress field and strain field in Cartesian coordinates. So therefore, we will see that they are non-symmetrical on Cartesian coordinates, because for cylindrical object, if we represent them in cylindrical coordinates, we will see a symmetry. Okay, so this is something that we can note down. Non-symmetrical because we used Cartesian coordinates. For cylindrical object. Okay, that's why it looks as though it is not symmetrical. However, if you look at the dislocation stress field for this screw from the z direction, okay, you will see that it is symmetrical. Okay, you will see something like this. Okay, so you will see that it is symmetrical from the z direction. Now, the reason why, because in cylindrical and Cartesian coordinates, the z direction usually means the same thing, in both the coordinates. Therefore, you will see that in z direction, when you're looking at the stress field for screw dislocation, you will see symmetry there. Okay. So now let's move on to the edge dislocation. So this one was screw. Let me just write screw somewhere so that you can. So now let's talk about edge dislocation. So we'll not derive the whole thing. I'll just write down the expression directly so that we don't waste time there. But you are free to go back, look at the books that have been suggested. You will find those directions there readily. Okay. So here epsilon sigma xx is equal to minus gb by 2 pi 1 minus nu times y 3x square plus y square divided by 4 divided by x square plus y square the whole square. Okay. Now sigma yy is equal to gb by 2 pi. Similar way, no negative sign, but okay. 4 x square minus y square okay. Then sigma xy will be equal to, so only non-diagonal component that we'll have here is the xy. Okay, gb divided by 2 pi times 1 minus mu. This part will be common all the time. X times x square minus y square divided by x square plus y square. Okay, and finally sigma zz, which will be equal to nu times sigma xx plus sigma yy, right, using our general relations between stresses, normal stresses, the relation between that. So minus gb nu divided by pi 1 minus nu into y times x square plus y square. Okay. So essentially we'll have sigma for h to be equal to, the stress tensor will have only these components, xx, sorry, xy will be there. Similarly, the strain tensor will also have the same components. Okay. One important thing you can note here is that this is exactly inverse of screw dislocation tensor, right? Because this has exactly the quantities present in the stress or strain tensor, which are not present in screw dislocation, and vice versa, right? So this is the importance of classifying H and screw dislocations, right? Because even though in real life we'll not have exact screw or exact edge all the time, we'll have like a mixed characteristics. By classifying them as edge character or screw character, it makes us very easy for us to solve problems, and then anything in between can be characterized by a combination of this. Okay, so we are covering all the stresses in either screw form or in edge form. Okay, so yeah, if I will draw the stress fields, how they will look like. So sigma xx will look something like this. Okay, this is how sigma xx will look. This is negative, this is positive. Now sigma yy will look little bit different. It will not be like xx. So we will have like a big region here and another big one here. Okay, this one is positive. The top dome is negative, bottom dome is positive. Okay, and then we'll have more along the other planes. So this will be positive, this will also be positive, these are negatives. Okay. The sigma xy will look something like this. It will be similar to sigma yy, but in the other direction. This is a little bit bigger. Yeah, and then you'll have again similar to last time, you'll have other directions. So here it will be positive, here it will be negative. Okay, and because we are able to draw all these three stresses, we can also draw hydrostatic state of stress, which will look exactly like sigma zz. Exactly like screws sigma xz and sigma yz. So it will look something like this. So it will look like this. Okay, this is your sigma hydrostatic. Okay. So now that we have talked about state of stresses and state of strains, let's calculate the energy associated with any dislocation. So we will not derive all the expressions. We will just talk about the final values directly. Okay. The derivation to an extent has been talked about in the videos, and also you can go back to the books and see the derivation in detail. But just essentially what we're trying to do is we are trying to break any dislocation. Okay, so let's say this is my dislocation. Okay, sorry. Let's say this is my dislocation line. I'll just represent it with line. This is my dislocation line. Okay, so around that line there'll be a region where most of my energy of the dislocation core will be concentrated. So this will be known as dislocation core energy. And outside this region, we'll have all the other energies represented as elastic energy for the particular body. Okay. Now core energy, again, it has some separate derivation. What we are interested is in elastic energy. Okay. Elastic energies basically can be found using the summation rule, right? You have half of sigma ij into epsilon ij giving you the energy. So that is what you can use directly. Okay. Half of epsilon ij sigma ij. So this form only you can use to find the energy. Let's remove the d. I'm not going to write the whole thing. Yeah. This is the form we can use. Okay. So in the end, my total energy would be equal to E core plus E elastic, right? So my energy for screw dislocation, energy for screw dislocation will be equal to GB square divided by 4 pi times ln of R by R naught. Okay. While my energy for edge dislocation will be equal to GB square divided by 4 pi times 1 by mu. So this only this extra term will come, 1 minus mu term will come. Then remaining is ln of R. So everything else is same, only this 1 minus mu term is coming, extra term is coming. Okay. So this is my elastic energy. Okay, let me just elastic energy for screw, elastic energy for edge. Okay. So my total energy, let's say I represent my E core energy to be equal to GB square times some B. Okay, GB square by 4 pi into B. Okay, so my total energy would look something like this. GB square for screw, this is for screw, okay. By 4 pi times ln of R by R naught plus B. This is my total energy for screw. Similarly, I can write the total energy for edge also. Okay. So my E total is equal to something like alpha times GB square. Some alpha term times GB square. Okay. Now this alpha terms generally varies from 0.5 to 1.5. So in most of the problems that you will see, if alpha is not given, you can just take it as 0.5 or 1 by 2. Okay. Just take it as 0.5 if it is not given. Or my total energy is proportional to the square of Burger's vector. Okay. So why we are not concerned with core energy? There is a reason to that. Okay. Why we are not concerned with total energy? So energy of this core, so this is something that you can note down. Energy of core, okay, is about 1/10 of the total energy of dislocation. So that is why we are not concerned with the core energy of the core. Okay. Another important thing that we have to take into account is a dislocation will always try to minimize its Burgers vector. It needs to have as small Burgers vector as possible because it is an extra amount of energy that it is costing in order to form that dislocation, right? Some extra stress or extra energy is present in the material. So if you want smaller amount of energy, like for smaller amount of energy, you will need to have smaller Burgers vector. So in order to minimize that, many a times what we will see is dislocation breaking down into Burgers vector. So essentially, if we want to calculate whether a dislocation will branch out or not, okay, we can see that if the Burgers vector is greater than the Burgers vector of the two new branches that have been formed, square of the Burgers vector, sorry, then we can say that the dislocation will branch out, right? Because my total energy is proportional to Burgers vector square. So if the Burgers vector for the branched out systems, the summation of Burgers vectors of the branched out system is lower than the summation, than the Burgers vector of the original dislocation, then it will branch out. Okay, so then you will see something like this. However, like I said previously, I've already mentioned previously, the branching can only be possible when the summation of Burgers vector is equal to 0, summation of the total Burgers vector. So the branching should happen in such a way that B1 should be equal to B2 plus B3. Okay, that needs to be conserved. This needs to be conserved. Okay. So now that we have seen energy for individual agent core dislocations, what could we say about energy of a mixed dislocation? So energy for a mixed dislocation, the elastic energy, you're talking about the elastic energy, not the core, is something like summation of the edge part and the screw part. Okay. Okay. So my total energy would look like, so my elastic energy would look like something like this: GB square by 4 pi. So this is an empirical formula people have derived. Okay, this is not always exact, but this is gives us a good assumption as to what energy we could have. Plus cos square theta. Okay, ln of r by r. Okay. One last thing that we need to discuss before we move on to problems for today. Actually, two things are left. Sorry, forgot about. Yeah. So let's talk about first the line tension associated with any dislocation. So what will happen when a dislocation, dislocation is getting formed? Now, essentially, dislocation is what is dislocation trying to do? It is trying to manifest the energy present within within the structure. Now, this energy could be present at different spots, right? Now, that will lead to bowing of a dislocation. However, a dislocation will always try to be in a straight line, right? Because bowing will cost an extra amount of energy. So that increases, this bowing essentially increases the energy of the dislocation, which the system will try to minimize. Okay. So because of this bowing happening and the system trying to minimize that thing, there will be an extra force or extra tension which will disallow it from increasing in size. Okay, so this extra tension or extra force that we are talking about is known as line tension for a dislocation. Okay. Okay. So how do we find this line tension? So let's now first draw dislocation. Okay. So if you are having a dislocation like this, let's say this is the center. We just do it a little bit better. Let's say this is a dislocation. Okay. And this is my d theta. This is my radius r. Okay. So this will be essentially d theta by 2. Same thing will happen here, d theta by 2. These are the angles. Okay. So the force that the dislocation is experiencing, the tension that is experiencing, is represented by this T. Okay. So in this direction it will be T sine d theta by 2. Right, in this direction. Just look at the geometry, you'll understand. This will be T sine d theta by 2. This T is equal to the energy for particular dislocation, right? The energy value that we have derived. Total energy, alpha GB square, right? So I can rewrite it as 2 T sine d theta by 2. Two T sine d theta by 2. Now what is this equal to? This thing that I have created here, T sine d theta by 2. What is this equal to? This is equal to the shear stress that is associated with this particular dislocation that is causing that bowing, right? So that will be tau times B dl. How am I getting this? How am I getting this? So in order for this bowing to happen, I need to apply some force F, right? Some force F, which is equal to tau times B, right? Because I'm writing tension in terms of not B, it's times dl. Sorry, yeah, tau times dl. Are you asking a question?
No.
Can you mute yourself?
Yeah.
Yeah. So like I was saying, there is a force that is causing this dislocation from that is allowing this dislocation to bow, right? That force can be given in terms of F times dF, okay, which is equal to tau times dl. Dl is basically this length. Okay. Now this F is equal to T by R. This force is equal to T by R. Here R is equal to Burgers vector. So I can write T is equal to tau B times dl. That is what I have written here. Right? But T in this particular case is in a particular direction. It is T times sine d theta. Okay, or d theta by 2. But that is acting along two directions. There is one here and then there is one here in this direction. Right? So there are two T's. So I can write 2T sine d theta by 2. But since theta is very small, I can change sine d theta by 2 to be equal to d theta by 2. So 2T d theta by 2 will be the final expression. Right? That is equal to 2B dl. Or I can rewrite it as T d theta will be equal to tau times B dl. right? So this is my expression. Now, if I interchange and rewrite this entire expression, this will be T by B times d theta by dl. Okay. So what we'll have finally is equal to tau is equal to alpha g b square. Sorry, I read alpha g b square divided by b into r, or alpha g b by r. So r here is representing this r. Okay, I've already drawn it for you, the radius of the Boeing. So this is my final expression for Boeing. So any kind of shear stress that is required to make a radius r in dislocation, internal or external shear stress, that is required in order to form this radius r, can be taken as this value for dislocation. Okay, so this causes your Boeing. One final concept that we will discuss, then we'll move on to problems. We'll discuss about glide in any dislocation. Okay, so there are certain rules associated with glide of dislocation. Okay, this is something that which we have to remember. There are certain rules that we have to keep in mind. First thing is, dislocations of opposite signs will always glide in the opposite direction. Okay, so this you can remember. If dislocations are of opposite sign, they will always glide in the opposite direction. And next thing that you have to remember is, for any given shear stress, slip will only take place in a particular direction. Okay, for any value of given shear stress. For any given value of shear stress, okay, slip will only take place in particular direction. In a particular direction, whether it's positive, negative, edge or screw dislocation, it does not matter. Okay, slip will happen only in one direction. It will not change direction suddenly. It will only happen along one particular direction. Okay. Finally, shear stress. Okay, the shear stress that is associated with any dislocation, or at least some part of this, or at least a part or component, or at least a component of it, must act in the slip plane in the direction of Burgers vector. In the direction of Burgers vector. Okay. Finally, depending on the type of dislocation that we are having, whether it's edge or screw, we will have a uniquely defined plane for glide, or whether we will not have a uniquely defined plane for glide. So an edge dislocation an edge dislocation will have a uniquely defined plane for glide. Okay, but screw will not. But screw dislocation will not. Okay. So what do we mean by this uniquely defined? Uniquely defined glide plane. What do we mean by this uniquely defined glide plane? Why do we say that they have a uniquely defined plane in which they will glide? Because in edge dislocation, what happens? What happens in edge dislocation? Your Burgers vector is perpendicular to your slip direction. Burgers vector is perpendicular. Dislocation line is perpendicular to your slip direction. Okay, or Burgers vector. Your dislocation line and Burgers vector are perpendicular. Let me just write perpendicular. So, because they're perpendicular, they will be uniquely defined. Right? There will be a particular direction in which this can glide. Essentially, glide should happen perpendicular to the dislocation line, right? So glide can only happen along the Burgers vector. That is why it is uniquely defined. But in screw dislocation, what is happening? Your Burgers vector and dislocation line are parallel, right? So therefore, this is not the only constraint that will define whether your glide will happen in a particular direction. You need to see that if there are other constraints that will also influence in which direction the glide will happen. Okay, so there are two directions in which glide can happen. So depending on some other constraints, you can see whether it will happen along one direction or the other. Okay, so with that, we'll come to the end of the concepts for today. Let's move on to the problems. Let me just open the problems. Okay. So first question they are asking, where and all can dislocations terminate? So the obvious answer where it cannot terminate is inside the grain. It cannot terminate inside the grain on its own, right? But it can obviously terminate at free surface. But I have also talked about how surface does not only mean just the end of a particular system, right? Surface can also mean jumping from one crystal to another. So that kind of surface is known as grain boundary or phase boundary. So those kind of surfaces also, the dislocation can also end. Right? So these are also the correct answers. Next they have asked, mark the correct statements for screw dislocation. So direction of dislocation line movement in screw dislocation is perpendicular to its Burger vector. That is correct, right? Dislocation line movement. They're not saying dislocation line. Dislocation line movement has to be perpendicular to Burgers vector. That is very right. Direction of dislocation line movement in screw dislocation is perpendicular to dislocation line. Again correct. Right? Step created when screw dislocation leaves the crystal is parallel to its Burgers vector. So when screw dislocation leaves the crystal, there is a step created. Is it parallel to the Burgers vector? think about it. When I rotate the crystal like this, and I create a screw dislocation. So screw dislocation will be along this direction, right? This kind of step will be created. So a step will be created like this. So is it parallel to the Burgers vector? Yes, because Burgers vector is also along this direction. Step is also created along this direction only. So yes, this is right. Last line is step created when screw dislocation leaves the crystal is perpendicular. That is wrong. Okay. Next question. A glide loop is shown in the figure below. Okay. And the Burgers vector lies in the plane of the paper. So Burgers vector is not perpendicular, it lies on the plane. So at different points they are asking what is the nature of the dislocation. Okay. So here we can directly see that nature of dislocation at point A and C is what? It is parallel to the Burgers vector, right? So it will be screw. And then at point B and D it is perpendicular, so it has to be H. So which option says H? Second one. So these are the two correct answers. Okay, so next question. Again, mark the correct statement in case of prismatic loop. So we already saw what kind of prismatic loop we have. So they are saying Burgers vectors lies perpendicular to the plane of the prismatic loop. That is correct. Burger vector will always lie perpendicular to the plane of the loop, right? That is true for whether it's prismatic or non-prismatic. So this is anyways correct. Now Burger vector lies in the plane of the prismatic loop is wrong. It is perpendicular, right? And the nature of the dislocation at every point on dislocation line of a prismatic loop is edge in nature. That is correct. It is edge. And finally, they are saying it is screw in nature. That is wrong because we can never have a loop with just screw because we need to have some points where there will be edge. Otherwise, the loop will never form. Okay. Next question. It's a problem. They are saying elastic strain energy associated with dislocation 1 is 2 times that of dislocation 2. Okay. So what they're saying is strain energy, which means E total for 1 is equal to 2 times E total for 2. Right? This is what they're saying. Which of the following statement can be independently true? So they have given us 4 statements. We have to find which of them can be true. So the first and the third options are relating the Burgers vector for 1 and 2, right? Now if energy is proportional to square of Burgers vector, right? So if E total 1 is equal to 2 times E total 2, then Burgers vector 1 will be equal to root 2 times of Burgers vector 2, right? So this is the third option. So first option is wrong, third option is right. So now they have given us specific cases. The second and the fourth option are specific cases. They're saying 1 is an edge dislocation and 2 is a screw dislocation in a material with Poisson's ratio 0.5. Okay. So we have energy, elastic energy associated with screw to be equal to GB square by 4 pi ln of R by R naught. Right? Just 1 second. Just a second. Seeing some issue. Okay, my screen is facing some issue. Just 1 second. Okay, I think my screen is back. Are you able to see my screen?
Yeah, I'm able to see.
Okay, okay. I think there was some issue with my recording also. I'll fix it anyway. Yeah, can you mute yourself? Thank you. Okay, so yeah, like I was saying, the solution here. Okay, so yeah, so for elastic energy for screw dislocation is given by GB square by 4 pi ln of R by R naught, while for edge dislocation it is given by the same exact thing. Just 1 by nu minus 1. In the denominator we'll have 1 minus nu term ln of R by R naught, right? So if we put nu is equal to 0.5, then we'll have for edge dislocation we'll have 1 minus 0.5. So there will be a 0.5 at the denominator, which will take to the top, so it will become 2 times whatever is the screw dislocation elastic energy, right? So we can write the first option is also correct, right? Now, last option, option D, they're asking us for a mixed dislocation characteristics. Okay. Now, if I substitute for this particular case, in for elastic energy for a mixed dislocation, E elastic for a mixed dislocation, I will have elastic for a mixed dislocation. I'll have Burgers vector 30 degrees. Since Burgers vector 30 degrees, whereas for 2 is screw dislocation. 1 is a mixed dislocation. So for mixed dislocation, it will be GB square by 4 pi times 1 minus nu cos square theta and divided by 1 minus nu ln of R by R naught. While 2 is a screw dislocation. Okay, so that's what they're saying. So if I solve this, if I substitute and I solve this, I will get GB square by 4 pi okay ln of R by R naught. Those terms are common. This is the exact term which is common to screw times something, right? So this times something is determined by this middle term. Let me just calculate that. Just give me a second. So it will be into 5 by 4. So this is screw dislocation times 5 by 4, which is again not correct. Therefore, this option D is not correct. Okay. Now, sixth question. While comparing pure screw and pure edge dislocation, the elastic energy per unit length of dislocation and line tension are higher for which one? So we know that in edge dislocation, we'll have a 1 minus nu terms in the denominator, right? Now this nu term, nu is essentially less than 1 always, right? So 1 minus nu will be less than 1. So in the so the denominator will have a term which is less than 1. So something divided by less than 1 will be equal to a greater term, right? So we'll know that elastic strain energy per unit length of dislocation will be higher for edge dislocation. Line tension is also dependent on this energy itself. So that will also be higher. So therefore, in both the cases, it will be higher for edge dislocation only. Okay. Next question, for a BCC material, select the possible slip planes for screw dislocation having Burgers vector A by 2, 1 by 1. 1, 1, 1. Okay. So which and all are possible? They are asking which and all are possible. Now, for glide to occur, right? The dot product of the Burgers vector and the slip plane should be 0. That is, it should be perpendicular, right? So the dot product should be 0. So in which cases will it be 0? So 1, 1, 1 times 1 minus 1, 3 will not be 0. 1, 0 minus 1 will be 0. So that one is correct. Minus 1, 1, 0 is also correct because it will be 1. Sorry, minus 1 plus 1 plus 0. So that will be also 0. 1, 2, 3 will not be correct. So that will also wrong. So you can just write dot product 1, 0 minus 1 dot 1, 1, 1. Sorry, your directions. It will be 1 plus 0 minus 1. Be 0. Same will true with minus 1, 1, 0 dotted with 1, 1, 1. This will also be 0. Okay? The other two cases will not be 0 in a similar fashion. Next question. Mark the correct statements regarding the motion of the dislocations. Okay. So, screw dislocations of opposite sign glide in opposite direction for a given shear stress. Again, that is correct. If you remember, just now we talked about glide. So, opposite signs will have to glide in the opposite directions. Edge dislocation has a uniquely defined glide plane. Again, we have talked about this. It is true. Because you have Burgers vector and the dislocation line perpendicular to each other, so it will be uniquely defined. For a given shear stress, slip direction is independent of nature of dislocation. That is correct. Slip direction will not be dependent on the nature of the dislocation. It will be dependent on other things, right? It will be dependent on which direction the Burgers vector is pointing towards. And only edge dislocation can glide while screw dislocations cannot glide. That is wrong. Both of the dislocations can glide. Okay. Next question, for a given, determine the elastic strain energy of a screw dislocation in copper. It is given that magnitude of Burgers vector and shear modulus are 0.25 and 48.3 GPa respectively. Assume multiplication factor of 0.5. So they have given us the value of G, the value of B, and they are asking us to find the elastic strain energy and multiplication factor alpha to be 0.5. So then it is very, very straightforward. Total strain energy will be equal to, let's write down the formula first, alpha G B square, right? So it will be equal to 0.5 into 48.3 into 10 power 9. Let's convert GPa into pascals so that we can write it in joule per meter, into Burgers vector, which is 0.25 into 10 power minus 9 whole square. Okay. So everything is in SI unit, so it will be joule per meter. You will get the final answer. So let me just calculate the answer. So I got final answer to be equal to 1.5 into 10 power minus 9. Yes, is there a doubt?
I was getting some 3.25. It is 3, not 1.2.
You are getting 3.25.
Yeah.
Can you recalculate and check?
Okay.
It is 0.5 into 48.3.
Okay.
10 power 9 into 0.25.
Okay.
Just check again.
Okay. Yeah.
It's I think you made a mistake in that 0.25 square. It is supposed to be squared.
Correct.
Yeah. So that there only I think. Just be careful while doing calculation. You know the formulas, but if you just make a small mistake, your final answer will be wrong. So.
Okay. Thank you.
Yeah. Okay. So let's come to the final question for today.
Okay.
Can you mute? Just some disturbances. Yeah. Thank you. So which of the following statements are true regarding edge dislocations? Direction of dislocation line movement is perpendicular to its Berger vector. That is correct. Direction of dislocation line movement is parallel to its Berger vector. That is wrong. Dislocation leaves by slip plane by the process of climb. That is right. In edge dislocation we will see climb, while in screw we will see cross slip. Right? We have discussed that. And then dislocation line is perpendicular to this Berger's vector. That is again correct. So dislocation line movement and dislocation line both are perpendicular. Okay. So yeah, these are all the things that we have covered for today. I hope you have caught up at least some portions of it, and remaining you can just look at the video again, or you can go back and read more.
Sure.
Yes. Okay. Yeah.
Thank
So
you. Thank you.
with that, we will like to end today's class. Okay. So thank you for attending.
Thank you. Thank you very much.
Okay. Thank you. If there are any doubts, you can ask in the subsequent class, or we can move on to the next topic again.
Sure. Thank you.
Okay. Okay. Thank you. Thank you.